Okay, hello. Happy Fridays. What I'm going to do is I'm going to give you a little bit more help to understand the concept in this chapter 5. Okay, so we defined the eigenvalues and eigenvectors of a matrix. So we're going to continue seeing what amazing properties of these these two quantities. Okay, so let's go back to my notebook so we can remind you the definition that we have. So step by step, carefully read these sections. As I told you, they are the best part of the course. So what we did, just remind you, we just defined the, we defined the eigenvectors. We are very much interested to see if we can write a matrix, if we can write a matrix as a scalar multiple of a vector, because that makes it very easy to operate with this matrix, okay? So if you can find a scalar like lambda, a number, like lambda is going to be called eigenvalues, means a proper value in German. Okay, so a scalar, a number lambda is going to be called eigenvalues if you can find a non-zero vector x that satisfies this condition. Okay, so if you have this condition and x is a non-zero vector, x lambda is going to be called eigenvalues and x is its corresponding eigenvectors. So the situation was how we're going to find it. We move it to the other side and we get the fact that you see this is what we did. Okay, so we realize that if you would like to have this identity x equal to the lambda x, you move it to the other side, you get this system, if you like, equal to the 0. And then what we did, this x is a non-zero vector. Since x is non-zero vector, we must make sure that this is not going to be invertible. You know that if you call this one b, bx equal to the 0, if b happened to be invertible, then x would be 0. But we want x to be a non-zero number. So the condition would be that a minus lambda I or lambda I minus a is going to be a singular matrix, means it's not invertible. And we know that the matrix is not invertible if the determinant of the matrix is 0. So for the condition to get satisfied for the lambda and x, you must have this one. That's of a minus lambda equal to the 0. We just put them together. The result's going to be a polynomial in lambda. This polynomial is going to be called characteristic polynomial. So it's going to be characteristic polynomial of the matrix of a matrix A. And it's clear that lambda is going to be eigenvalue if and only if, of course, lambda is the 0 of this polynomial. So basically to find it, we are going to get through these conditions. We get a polynomial, we let it equal to the 0, we get the solutions. You know that this polynomial in science, they want to make sure that in physics, quantum mechanics, we want to make sure that this polynomial would have a solution. If you consider complex numbers, then you know that if you consider complex numbers, then any polynomial or any equation would have a solution. Okay, p lambda, the degree is n. If you accept the complex numbers, so you are going to have n solutions. So n solutions, so this means always you are going to have eigenvalues. But for the time being, we are going to ignore the complex one. We come back to the complex because the operation getting a little bit messy, but it's not bad. We talk about it. So I just want to guarantee that this equation would have a solution, right, if you work with the complex numbers. So for the time being, just finding these are going to be important for us. Give you example, and we did it. It's a 2 by 2 before the a minus lambda I, and we are going to do today some more before you. So we find these lambdas, and then we go and find the corresponding vectors. Okay, so this is the one that I did. There are some technical parts we talk about it, and we are going to see more of these today. Okay, so that is going to be the classic part. So we can look to some properties of the eigenvalues. These properties mostly are problems in your book, but I would like to put them together so that we have them in one setting. We may ask you to prove it, although I prove it for you, but we may ask you to prove it, so make sure you know them, and we are going to use them, okay? So we are not done with that 5.1. So what I do, I would like to give you some of the properties in one collection or one place. So what can you tell us, or what can you tell us about the properties of these eigenvalues, eigenvectors, okay? So what is properties? Well-known ones. Properties of eigenvalues, those lambdas, and their corresponding eigenvectors, okay? Eigenvectors. I'm going to list those popular ones, and we're going to use all of them. So what's going to be the first one? You see, the first one is, we would like to see what is going to be a relation between eigenvalues of a matrix and its powers. So sometimes you are interested in matrix A, you may be interested in matrix A squared, A to the third, A to the fourth. We realize that if, let's write it down as we talk about it, if lambda, this is the first property. This is one of the problem in your book. If lambda is an okay, if it's going to be an eigenvalue of A, eigenvalue of A, I mean of a matrix A, of course, let's say of the matrix, we mean the matrix, of course, matrix A. Okay, this is not going to work anymore. I need to bring another one. So if lambda is an eigenvalue of the matrix A with the, and you know that the matrix is a square matrix and by it, with the corresponding eigenvectors, okay, with the corresponding, so its eigenvalue, then we can find the eigenvector corresponding eigenvector x. If it's given to you, then this is a nice part. Then lambda to the k, lambda square, lambda to the third, to the fourth, lambda to the k is an eigenvalue, okay, eigenvalue of the matrix, A raised to k, ak, with the same eigenvalues, eigenvectors, with the same, okay, this is going to be, I'm sorry about this, with the same eigenvector, vector x for any power, for any, okay, for any positive integer, k. We are going to use this one when we get to the next section. So we prove it, we keep it, and you can use it anytime you like, okay? So if lambda is an eigenvalue of a matrix A with the eigenvector of the x, lambda squared is going to be eigenvalues of A squared. Lambda to the third for the A cube. So in general, lambda to the K is going to be eigenvalues of the A to the K. An interesting point is with the same eigenvectors. So the eigenvectors won't change, but you are going to get the powers of the lambda, okay? So let's prove it. Again, as I told you, we may give you a specific power and we ask you to prove it on the test for us. So let's see what is going to be the, okay, what's the proof of this fact? Let's see what you have. You see, lambda is the eigenvalue of A with the eigenvector of X. So you can suppose that AX is equal to the lambda X. This is given to you, okay? This is the assumption. So you want to consider the powers, okay? If this is going to be the case, then let's try one power and one easy one to see. What is going to be A square of X? You know that the A square of a matrix means A times A is a composition function. Remember, A times AX, this is it. But what is the AX? You see the AX is lambda X. So this AX is going to be lambda X. So this is going to be equal to the A times what? A times lambda X. A times lambda X. Okay, but remember the lambda is a scalar and A is like a transformation. So we can pull out the lambda. Okay, so it's going to be A times AX. So this is going to be the A and this is going to be lambda X. So we bring the lambda out. So that give a lambda, okay, lambda AX. But what is AX? You see the AX? AX is equal to the lambda X again. So this is going to be lambda times lambda X, which is going to be lambda square of X. You see, nice. A square of X is equal to what? Is lambda square of X. And remember, X is a non-zero vector. Okay, so what does it mean? This means simply, this is it. Therefore, this means lambda squared. Lambda squared is an eigenvalue of lambda of A squared. And eigenvalue of A squared with what? With the eigenvectors X. With the eigenvector X. Okay, so what we did, we just prove it for A squared. So we can do the same thing for the 8 cubed, A to the third, A to the fourth, and in general, you can get that conclusions. So we say similarly, you must use a mathematical induction to prove it, but we accepted that it's the same procedure that I did. So we can say that for any k in general. In general, now you can have that if you have a k of x, you can do the same procedure. You pull out one ak minus 1, ak minus 2, etc. So in general, a to the kx is going to be similarly like lambda to the kx. Okay, and so lambda k is going to be what? Is an eigenvector, is an eigenvalue of a to the k with what? With the same vector. Okay, same vector x. So it's a kind of proof of the, we just proved it for a squared. The rest are going to be the same, so we accept it in this format. Okay, so that's the first condition. It's very useful. You can use it anytime you like. If lambda is an eigenvector of the eigenvalues of the a, so a lambda square is for the a square, and lambda to the k is going to be this. And the good thing about it, the vector won't change. The vector x that works for a would be also good for the any power of a. That's the first property. Very useful. Okay, is it nice? That gives us better understanding of the definition that we have. So what's the second one? Again, the problem in your book. What is going to be the second property? The second property is that we want to know what's a relationship between eigenvalue of a matrix A, and in case A is invertible, with the eigenvalue of A inverse. Okay, so suppose the matrix A is invertible and lambda is going to be its eigenvalue. So we can prove that 1 over lambda, the inverse of the lambda, 1 over lambda is going to be what? 1 over lambda is going to be eigenvalues of A inverse. Okay, again with the same vector. So this is the second that we are going to check. If lambda is an eigen, okay, it's going to be an eigenvalue of A, of let's say of an invertible. The matrix must be invertible. Of an invertible matrix A, okay, matrix A, then in this case, we can prove that the lambda is not equal to the 0. Okay, lambda is not equal to the 0, and in fact, 1 over lambda. 1 over lambda is going to be an eigenvalue of what? Of the matrix, of the matrix, of the matrix A inverse. Okay, inverse, and good thing about it is with the, okay, again, with the same eigen, okay, same eigenvector. Okay, that's a second problem that we have. It's very useful and we're going to use it anytime you like, but make sure you know the proof. We may ask you to prove it. Okay, let's see how we're going to prove it. Like the one that we did. Prove. Let's start with the given definition. What do you have? We have that, okay, we have that lambda is going to be eigenvalue of the A. So we suppose that AX is equal to the lambda X. Okay, AX equal to the lambda X. Then what we would like to do, we'd like to change this one into the A inverse, if you like. Okay, A inverse. So A is invertible. Okay, A equal to the lambda X, and since A is invertible, okay, A is invertible. So what we have, multiply both sides by A inverse. You see, if we multiply both sides by A inverse, we have what? A inverse of AX is equal to the A inverse of lambda X. You know that A inverse times A is going to be identity. So this is going to be identity, and identity times X would be just X. Over here, lambda is what? Lambda is a scalar, and A inverse is linear. So you pull out the lambda, is going to be lambda times A inverse, okay, times lambda times A inverse of X, A inverse of X. Okay, so this is the situation we're going to have. Since X is a non-zero number, so this means the lambda must be non-zero. Okay, lambda must be non-zero. So we can divide both sides by lambda. Okay, so if we divide by lambda, what is going to be the result? It's like you are going to have like 1 over lambda. X is equal to, okay, is equal to what? If we divide by lambda, is equal to the A inverse of X. So what we proved that the A inverse of X is simply equal to the 1 over lambda. 1 over lambda times X. So what does it mean? This means 1 over lambda is an eigenvalue of A inverse, and the X is going to be eigenvector. And that's exactly what we want to prove. Okay, so I write it down here. So therefore 1 over lambda is an eigenvalue of A inverse with what? With the same eigenvector vector X. That's it. Nice proof, easy and nice. Okay, again, it's one more problem in your book. So if A is invertible and lambda is going to be eigenvalue of A, then lambda inverse, the inverse of the lambda, or the reciprocal of the lambda, because lambda is a number. The reciprocal of the lambda, 1 over lambda, is going to be eigenvalue of A inverse. And the other interesting thing is their eigenvectors are going to be the same. Whatever you use for A, you are going to use for the A inverse too. Okay, so that's another famous property of the eigenvalues. Okay, so 1, 2. What's going to be third one? This third one again is interesting. It's kind of algebra. So the third one, remember we talk about a characteristic polynomial. Remember that polynomial in terms of the lambda, we call it a characteristic polynomial. This characteristic polynomial would have some nice property. So I'm going to explain it as there is going to be a formula. I'm going to find it, and then you can use it. You have two problems in your book. So let's observe this characteristic polynomial. Okay, so suppose this is it, the one that we have. Okay, so suppose P of lambda equal to lambda n. This is a polynomial of degree n, Cn minus 1, just a number, lambda to the n minus 1, and you just keep going, that. We get to the C1 lambda plus C0. C0 would be the constant there. Okay, suppose this is a characteristic polynomial of it, okay? Suppose is a, you know that you form that of lambda I minus a equal to the 0, we get to this one. Suppose P lambda is a characteristic, is going to be a characteristic, okay, characteristic polynomial of the matrix, okay, of the matrix n by n matrix, of the matrix A, of a matrix A, okay? You can talk about quite a lot about this polynomial, but the one that I'm going to be interested in, I want to know what's going to be, you know, if this is going to be the case, what is P of 0, okay? So you note that this is the one that we are interested in. So what is going to be P of 0? You see P of 0, if you replace lambda by 0, everything would be 0 except the last term, the constant term, okay? Except the constant term. So the P of 0, you know that it's going to be a constant term. But we have another the definition of this. You see bad? What is bad? You know that the P lambda, how are we going to get the P lambda? Remember, P lambda is the determinant. Is going to be the determinant of what? Determinant of lambda I minus a. That was the definition. When you distribute, you know, expand this determinant of the lambda I minus a, that give you the polynomials. Okay, let's find out what is going to be lambda 0 now. So what's going to be lambda 0? If you replace the lambda by 0, that gives you something nice. You see, that gives you the determinant of, this would be 0 minus a. 0 minus a would be just 0. So that gives you what? That gives you the determinant of a negative a. Okay, so what we have is that the P of 0. P of 0 is the determinant of the depth of a negative a. Remember, we did this one before. If you have a number here, you can pull it out of the determinant, but you have to raise it to the n. Remember, A is an n by n matrix. We did this one before. So this would be equal to the negative 1 to the n. Negative 1 to the n times the determinant of A. Okay, so P of 0. So your P of 0 is going to be the determinant of negative 1 to the net A. But on the other hand, P of 0 is C0. So if you connect these two together, you have a very nice identity. What is that identity? The identity is that the constant term in the characteristic polynomial is simply equal to the negative 1 to the n times the determinant of the A. If you divide by negative 1 to the n, this is either a positive one or a negative one. So if you divide, that gives you the determinant of A, is going to be -1 to the n C naught. You see, very nice property. This means if you have the characteristic polynomial, and if you find P of 0, the constant term of that characteristic polynomial is the kind of determinant of a matrix. Okay, so it's fun. It's one problem again in your book. Just wanted to how to connect them together. Okay, so the actual problem in your book is a two part. This is one of them. The other part they ask you for this one. So you can use this one anytime you like. So what they ask is this. They give you this polynomial. They suppose that the P of lambda is equal to the lambda cube minus 2 lambda squared plus lambda plus 5. Okay, they want you to suppose that this is a characteristic, is going to be a characteristic of what? It's a characteristic polynomial, okay, polynomial of a matrix A. Okay, you realized from 3 that this matrix is a 3 by 3 matrix, but they ask you find the determinant of A. You don't have the matrix, but you can find the determinant of the matrix. Why? Because this is it. Determinant of the A is a -1 to the n times the constant term. The constant term over here is 5. The constant term is 5, and then you just substitute, get your result. So the solution is going to be, okay, the solution is going to be from this polynomial. You know that this is n is equal to 3, the degree, the constant term is equal to the 5. So this is it. So now you have the fact that the determinant of the A. So the determinant of the A is going to be what? Is a -1 to the n times C0. So it's going to be -1 to the third times 5. -1 to the third would be -1, so that gives you a -5. So the determinant of your matrix is simply -5. This polynomial got some other properties, some special cases that we're going to see in future. Okay, so these some very small points, small problems, but give you a little bit insight property of the eigenvalues to get a feeling. The practical one is you just form as we did it the other day, but we would like you to get these some of these small points, small proofs to get a better understanding of the eigenvalues and their relationship that we have. Okay, so this is 5.1 now. You are done with the 5.1. Okay, so what's next? Why we are such a, we have, so interested, if you like, in these eigenvalues. As I told you, there are many properties of the eigenvalues that we're going to use, but there is one that is very popular and used in quantum mechanics. Okay, all nice mathematical modeling would use this property. What is this property that we're going to talk about it? Remember, at the beginning, we defined a special matrix and we call it a diagonal metric. Remember the diagonal matrix? A diagonal matrix is a matrix such that this is the main diagonal of a matrix. Okay, we call it diagonal matrix if everywhere else going to be 0. Okay, so if all the terms, all the entries of a matrix except the one on the main diagonal happen to be 0, this matrix is called diagonal metric. As we did it before, it's very easy to multiply, to work with this diagonal matrix. So what is going to be the idea of that we are going to talk about it? The idea that we're going to talk about it is that if you give me any matrix, I can change that matrix somehow to a diagonal one. See, such an interesting result, because it's easy to work with the diagonal one. Okay, so that is form a great theorem, in linear algebra, that you are not going to have it. We call it a spectral theorem. Okay, spectral mapping theorem or a spectral theorem that will tell you that in order to study these matrices or this linear transformation, you don't have to study the complicated one, because by means of this theorem, we can change into the, all the complicated one to some easy one. So that gives us great tools to be able, of course, it's not equal to, you see, if I give me a matrix A, I cannot show that that matrix A is equal to the, equal to a diagonal matrix. I have to do some algebraic format, okay, some actions, but we use some expression, we call it similarity. So we are going to eventually prove that if you give me any matrix, with a special condition, of course, if you give me any matrix, then I can show you that I can find a diagonal matrix that's going to be similar to the A. Similar means similar in some operation. So the operation that you need to do with A, you can do it with that similar part, with the diagonal part. Okay, so that's a great section. 5.2, very dense section, quite interesting one. So that's why I want to give you all the details. Okay, at the end of the day, it's just one problem. It's very nice to understand this one, and that costs quite a lot in, if you're measuring, if you want to get advanced degree or upper division courses, if you like, in physics or in quantum mechanics or electrical engineering, you do need these type of operations. So pay attention and read it carefully, but you'll be able to do it because it's just two problems. But make sure you understand the concept. Okay, so this is a section 5.2. Let's see how far we can go. I just want to give you something, so you'll be able to quickly look at it. So we want to change our matrix into the diagonal matrix. This position is the title of this section, and we are going to explain it. We are going to call it diagonalization, if you like. Diagonalization. That's a changing, the given matrix into the diagonal matrix. Okay, let's remind ourselves that what is the diagonal matrix? Just refresh our memory, then we get to that. Okay, so remind you. Note that n by n, all the matrices are going to be square. Okay, n by n matrix D. Remember, D is going to be called, D is called a diagonal matrix, a diagonal matrix, if, okay, if all entries, okay, if all entries not on the not on the main diagonal, okay, its main diagonal are zeros. Okay, everything off the main diagonal must be zero. So this is going to be the matrix D. So the matrix D is going to be equal to, okay, so we have the D1, if you like. This is a D1, this is the D2, okay, D3, etc. So that will take us to the Dn, and this is going to be our matrix. Okay, this is the matrix, but everywhere else we get all zeros. Okay, some of these numbers can also be zero, but not all of them. Okay, so this is going to be called a diagonal matrix. Got many properties. The popular properties that we are going to use and we are going to be interested in, if you want to raise it to anything, if you want to square it, you just square these numbers. If you want to raise it to the k, you just, raising this to the k. That will help you because the powers of a matrix is the one that we are interested in. We are going to show you that if you want to find the power of a matrix A, you can find something similar like D and do the powering over here. So that's why we remind you this. Okay, so let's remind you that, note that, okay, note that in this case, okay, in this case, for any non-zero integer, non-zero integer k, we are going to have, okay, what we have, if you would like to get d to the k, you just raise these numbers to the k. Okay, so it's going to be d1 to the k, d2 to the k, and just getting to the dn to the k, and everywhere else 0. Okay, so that's one property of these matrices that we are going to be interested in. Okay, now we are going to have a question to answer. So what is that question? That's the one that I talk about it. So what is the question? Question is that if you give me a matrix A, I can change it somehow to the, I can show that this is similar to one of these matrices, okay, which is a great deal. So what's the question? The question is we can show, or we show, okay, let's say we can show, or one can show, we can show that if A is going to be is an n by n matrix, n by n matrix, okay, matrix which, this is the condition, which has, okay, which has n distinct, not equal to, distinct eigenvalues, eigenvalues, lambda 1, lambda 2 to the lambda n. Okay, eigenvalues, then A will be, let's say, similar. What does similar mean? We are going to talk about it later. Similar, like of. Okay, so which has n distinct eigenvalues, then A will be, okay, then A will be similar to what? To a diagonal matrix. A diagonal matrix D. And we are going to give a formula exactly in order to find it. Okay, so that's the idea. Similar means a copy, if you like. I'm going to define it in a minute. So what does it mean by the similar one? Okay, let's see if we can make this one better. Let me lose it, but we may get something better. Okay, a little bit better. So that's the idea of this argument, and that's where the eigenvalues is coming from. Okay, and now, so what we are going to do is to answer this question. First, we are going to argue that what do you mean by similar? Okay, what do you mean by similar? What is the similarity defined in the terms of the matrix? Okay, so let's take care of this one first, and then we answer the question. So what is similar mean? You have a number of the problem on this one in your book. What is similar matrices. Now, what's this? Now, if two matrices are given, if A and B are going to be, all the matrices are going to be a square, are n by n matrices, okay, n by n matrices, then matrix B is set to be similar, set to be, okay, similar, okay, similar to A, okay, B similar to A. B similar to A if this condition is satisfied. If there is going to be, you need somebody to be, involved to make this similarity, or something. If there is an invertible, okay, an invertible matrix P, okay, matrix P such that this condition satisfied. B is equal to P inverse times A times P. This is a definition of the similarity. Okay, so two matrices, A and the B, are going to be similar to each other. Okay, similar to each other if you can find an invertible matrix P that this condition satisfy, if you like. Okay, so what we do, we use, this is the notation that I'm going to use to make things easier. This is a kind of operation that we're going to have. So we write, if you like, this is it. B is similar, not equal to, similar to A if and only if. If and only what? There is a matrix, invertible matrix, of course. Okay, there is an invertible matrix P such that B is equal to P inverse AP. Okay, they are not equal to each other, but there is something, okay, they are going to be equal to each other by the third person, by the third matrix, if you like. Okay, so this is the notion for the similarity. Now, there are, when we write this type of idea like equality, you see, we have something like if A equal to B, then B is equal to A. They say this identity is symmetric. Or we have another one, we say that if A is equal to B, B is equal to C, A is equal to C. This is another, property that we have. So just write one of them so that you're not going to worry about which one is going to be one. Okay, so we just quickly emphasize that this property is symmetric. Okay, so what is symmetric means? Note that will help us. Okay, note that the similarity property, the similarity, okay, it's a similarity property. Okay, similarity property is symmetric. Symmetric means B is similar to A if and only if A is similar to B. Okay, so you can use either one when you want to prove or to talk about it. And this is not difficult to prove, you see, because Let's see it. You see, the reason is that if you see, if you get the first one, if B is equal to the P inverse of AP, okay, you can easily pull out the A. Remember, we talked about this type of ideas. If this is going to be the case, multiply from, you want to release the A, you have to multiply by P from the left and the P inverse from the right. So it's going to be P, B, PB, P inverse, because this is going to be P inverse, A, P inverse. We did this type of problems before. So if you put these together, you see this is going to be I would disappear. Okay, and this would be I. So the result simply is A. So you get the fact that A is equal to the B inverse. Okay, so remember B was similar to A, but if you would like to get the definition like the inverse that you have, you can cheat. You can cheat and write this one as A equal to, instead of P, you can write a P inverse of the inverse. And this is going to be the B that you have, and this is a P inverse. Okay, now you can call the P inverse something like Q. So now you have A equal to Q inverse of the BQ. You see, you just make up the formula for you. So this means, so A is similar, okay, is similar to B. Okay, so this means when we use it, don't worry about which one are going to write first. You write the one that you are going to be interested in, okay? So you see, this is the one. I start with the B equal to the P inverse AB. I change it to the A equal to the something inverse, you see, Q inverse BQ. So this means B is similar to A. This means A is similar to B. So basically, we got this result that, okay, so if you like, so I finish this one. So A is similar to B if and only if B is similar to A. It's easy fact, but that will help us from time to time that we are going to know. We are going to use it. Okay, there are again some problems in your book related to this property that we write over here. If you remember at the beginning of the course, I think quiz one, or I talk about the determinant of this, remember? So if you want to find the determinant of P inverse AP, the determinant was the same as the determinant of the A. And this type of property that we did before, and we are going to be finding useful. So I give you one remark, and I'm going to use this remark later. So what is this remark? The first one is exactly the determinant that we give you on that quiz. So look at this one. If you want to find the determinant of the P inverse of the AP, okay, you know the determinant is a multiplicative. So it's going to be the determinant of the P inverse times the determinant of the A times the determinant of the P. But remember, the determinant of the P inverse is just a number, is a reciprocal of this number. So this is going to be what? So this is going to be the determinant of the, you did it in one of the tests, determinant of the P, then inverse, and this is the det of A, this is the det of P. These are numbers, so you can, they are commutative, so you put them together, determinant of the P inverse, determinant of the P, and the determinant of the A. This is equal to the 1, because one of them is a reciprocal of the other one. So the result is simply determinant of A. Okay, so we know it, but we just confirm it again. determinant of the P inverse of the AP is equal to the determinant of the A. That is going to be the first property. Okay. So this is one. You may wonder why I proved this one. I proved this one because we are interested in what? Interested in eigenvalues. The eigenvalues, you see, these determinants are the same. A is one matrix, P inverse AP is the other matrix. So if you want to find the eigenvalues of the east one, remember, you have to consider the determinant of the A minus lambda I. If you want to consider this one, it's going to be P inverse of AP minus lambda I. This identity tells you that these two matrices would have the same eigenvalues, which is going to be very useful. Okay, so the next one is the determinant of, you can call this one B. It's the B minus lambda I. So it's going to be determinant of P inverse of AP minus lambda I is the same as determinant of, okay, I can prove it for you. You see, I want to show that this is the same as this one. Okay, so this is what we are going to do. What I do is I want to factor out something. So you see, this is the one. So what I do is, you know that these are numbers, lambda I. So what can I do to simplify this one is I can write the same thing here. You see, if I write the P inverse of the lambda I times P, they are the same because P inverse would be identity. But that will help you. That will help you to what? To kind of factor out. Okay, so this is going to be, you can put them together if you like. Okay, so you can factor out. This is going to be kind of, if you factor it out, you get a P inverse. It's going to be the same as the determinant of the P inverse A minus lambda I times P. You see, if you multiply together, exactly give you this one over here. Okay, and again, use this property that we did on the top. So that give you the determinant of A minus lambda I. Okay, because when you distribute determinant, the determinant of the P inverse and the P would cancel out, you get this one. So what does it mean? This means, that's very important one, the P inverse of AP and the matrix A have the same eigenvalues, the same eigenvalues. Again, these are a small point, but these are problems in your book. Just, help you to get a good understanding of this. Okay, so what we did in the first part, we defined that the determinant of the A and the P inverse AP is the same. That's easy. Now we want to focus on the eigenvalues. Remember, the eigenvalues of a vector is just determinant of A minus lambda I. So I consider P inverse AP minus lambda I. So I put them together nicely. I just, this is the first one. I changed this one into the similar thing. Here's the P inverse and the P would cancel out. So I haven't done anything wrong. But I can factor out if you like. P inverse from the left, P from the right. So in between, I get A minus lambda I. But the determinant of the P inverse, this is it. That gives you the determinant of the, the middle one, A minus lambda I. So as you can see, this is going to be, this equation would give you characteristic polynomial of P inverse AP, and that would give you characteristic polynomial of the A. So when the characteristic polynomials, those P lambdas, are going to be the same, so this means you are going to have the same, okay, the same eigenvalues. So it's in a kind of nice observation and help you for those problems that you have. Okay, so what is the problem? Remember, the problem was you give me a matrix A. I can prove that I can have a diagonal matrix D that is similar to A. Similar to the A means A is equal to the, or D is equal to the P inverse IP. I'm going to show you how I'm going to do it. Okay, so we are ready for that. This is it. Again, the procedure we explained at the end, but we would like to get through it, a little bit proof that give you better understanding of these ideas. So what is, if you can do it, if you can diagonalize the matrix, we have a special name for it. So what is that name? The name is diagonalization. Okay, diagonalization, if you like. Zibel. I think it's the way we write it down. Matrices. So this means the matrix that can be diagonalized. Okay. So this is it. What this definition means? This definition means an n by n by n matrix. Matrix A is said to be, okay, is said to be diagonalized, diagonalizable, diagonalizable if A is similar to a diagonal metric. If A is similar, it's going to be similar to a diagonal matrix D. That's the, when we say it, we can diagonalize it. So this means, the similarity. So this means in this case, there must be a third matrix. Remember, in this case, there is, okay, there is an invertible, okay, an invertible matrix, P such that, just a definition of a similarity, such that P inverse of A, P is equal to D. That's it. So you give me a matrix, I change it somehow to a diagonal one. You see, it's not going to be exactly the same. It's going to be similar. Okay, this is going to be, this is going to be the definition of a matrix to be able to, if you be able to diagonalize a matrix, we say, oh, it's a diagonalizable, if you like, to get this number. Okay, so what is the plan? That's it. Tell us, what is this D and what is this P? Okay, what is this T and what is this P? If we know it, then as soon as you give me a matrix, I can form the D and I form the P inverse and then get this confirmation right away. Now, the theorem is going to be, you see, there is only one condition. The condition is a matrix would given to, this is a matrix, n by n matrix. We talk about it. Would have eigenvalues. If the matrix A, n by n matrix, would have n distinct, okay, eigenvalues. So this means lambda 1, lambda 2, lambda 3 to lambda n. Okay, n distinct eigenvalues. This matrix D, diagonal one, is going to be a matrix, diagonal matrix, whose entries on the main diagonal is all those eigenvalues that we talked about. Okay, so D is going to be, instead of say D1, D2 to the Dn, is going to be lambda 1, lambda 2, lambda 3 to lambda. That's a D. How about P? Remember, each eigenvalue would have an eigenvector. Each eigenvalue would have an eigenvector. So what you're going to do is, you are going to find the eigenvalues of A. And then the eigenvectors corresponds to those lambdas. You find those eigenvectors, you are going to put those eigenvectors as the column matrix of the P. If you write it down as the column matrix of the P, then this condition will satisfy. And A is similar to the diagonal matrix. Okay, so I repeat it again and I write it down. I prove it for you. If you give me an A, n by n matrix A, and if I can, this is the only condition, if I can find the eigenvalues of A, and if I can have n distinct eigenvalues. So this means it's n by n. So I get lambda 1, lambda 2, lambda 3 to lambda n, because I need to form this n by n. Then the matrix D is going to be diagonal matrix whose main entries are eigenvalues, lambda 1, lambda 2 to the lambda n. The matrix P is going to be a matrix whose columns are eigenvectors. So if you form it, then you can confirm that this condition is satisfied. And this is your job. You one of these matrices, it takes a little bit of time. 2 by 2 is fine. Even 3 by 3 takes time. But we be patient and we do it because it's good for us. Okay, so that's the main. So I'm going to write it down for you. I try to give you a proof, okay, and then one example. Let's see what is going to be the case, okay, because this is, as I told you, this is one of the central result in linear algebra. So that's why we don't want to just skip it really. We want to get to it, to understand it, because that will help you to see that this, how beautiful these topics are going to be. And then you'll be surprised the number of the applications that you are going to have with this just easy concept that you're going to have here, especially if you are, most of you would really come to science major. So in those disciplines, quite a lot of these ideas. Okay, so let's get this theorem that I talked about it. This theorem would be the roadmap, okay, of finding it, but in practice, you have to find it for us. So what's the theorem? The theorem is going to be, suppose you give me a matrix. So suppose A is an n by n. Okay, n by n matrix. You give me this one, okay? Now the condition that we need to impose is this one. If A has n linearly independent, okay, linearly independent eigenvectors. Remember, you need those eigenvectors to form the P. Eigenvectors, then A, that's it, is diagonalizable. That's it. Very easy theorem. Okay, we focus on the eigenvalues, not the eigen, these are going to be eigenvectors. We should have distinct eigenvectors so that they be able to form the P over here. So if A is going to be an n by n matrix, then if you can find the eigenvectors of A, if they are going to be distinct, automatically they are going to be linearly independent, okay? So in that case, we want to show that the A is going to be diagonalized. So diagonalized means I can find the matrix P and the D that satisfy this condition. So you should tell us how you are going to find those. So we continue, we say that the matrix, okay, the matrix, that theorem so far means it's possible. So give us a practical method so that we be able to do it. So that's practical method. The matrix P whose columns. Okay, whose columns consist of eigenvectors, consist of n linearly independent, again, linearly independent, linearly independent eigenvectors, eigenvectors of A, okay, can be used to give what? To give a diagonal matrix, to give a diagonal matrix, matrix D, where what is formula for the D? Where D is equal to P inverse of the AP. This is how we form the D. We form the D. Then when we form it, we realize that, the diagonal, okay, the diagonal elements of D, all the members of the main diagonals are eigenvalues of the matrix. Okay, will be D eigenvectors, eigenvalues of A. See, that's a roadmap for for your theorems. So as you know the theorem, you can write the D right away. So you find the eigenvalues, okay? Then the D would be what? Would be a diagonal matrix whose main diagonal consists of eigenvalues. This is a theorem that gives you the construction, but in practice we can do it. We can do it right away to get these numbers. Now, you may not believe it, but it's interesting and not difficult to prove it. Okay, so I'll give you a summary of proof if you like. Just give you a good understanding of a theorem. Otherwise, we are not going to ask you to prove it, but why not? Let's see how we can connect, okay, to get this great theorem over here. Okay, so let's see. So we start with the matrix A, okay? Just for your information, we are not going to ask you to prove, but again, it's nice to be able to see it. How are we going to check it? Okay, there you are. What's the proof? I'll be given a matrix A, okay, and I will have eigenvectors and the eigenvalues. So there you are. Suppose A have, A has, this is it, A has eigenvalues, this is it, lambda 1, lambda 2, lambda 3, up to the lambda n. Okay, these are going to be the case with corresponding eigenvectors, with corresponding eigenvectors. These are the ones that you can quickly find. This is your job to find them, okay? I'm going to call them P1, not X, P1, P2, up to the Pn. That's it. So you give me the matrix, I provide both of them, and this is your job to provide it. Now, what is the claim? The claim is the matrix P. How are we going to build matrix P? These eigenvectors, you write them as a column matrix, you put them together, that should be the P that we are interested in. Okay, so set up the P. Okay, set up the P in this step. Suppose P. As we go on, we understand how we're going to do it when the example is given. Suppose P is a matrix. P is a matrix whose columns are those eigenvectors. Whose columns are P1, the first vector, P2, up to the Pn. So this is the matrix P that you're going to form for us. The matrix P is going to be a matrix whose column are P1, the first vector, then we get a P2, the second vector, that to get a P. This is a matrix. Okay, so you get the eigenvalues. You find the eigenvectors. You put the eigenvectors as a column matrix, you get a P. Now you have to prove. You have to prove what? So this is P. Now what's D? D is going to be a diagonal matrix whose entries are eigenvalues. Let D be a diagonal. Okay, a diagonal matrix. Diagonal matrix defined by what? Defined by, this is the D. The entries are eigenvalues. Lambda 1, lambda 2, okay, lambda 3, up to the lambda n. This is going to be everywhere else, we get the 0. Okay? So, what we need to prove? You need to prove that theorem, P inverse A, P is going to be equal to the, okay, equal to the D. So let's prove it. If it's going to be the case, now the proof. Look at this one. Then multiply A and the P together. All of them are metrics, okay? So this is going to be A. This is what? This is going to be a matrix whose columns are those eigenvectors. So it's going to be A times what? A times the matrix P1, P2, up to the Pn. This is it. Now, when you multiply them together, the result's going to be a matrix again. Okay, the result can be a matrix. The matrix are going to write that matrix. When you want to multiply, remember you multiply what? Each row times column. You see, row times column, we get the first number. Row times column, we get the second number, etc. So this is going to be like a new matrix would be like the one that you multiply the matrix A by the first column, P1. Then you multiply by the second column, A, P2, and you just keep going. You multiply by the n column. You see, it's going to be the result. Okay, these are two matrices. You multiply them together. So this is the multiplication of two vectors, two matrices. Now, what else? Remember, these are eigenvectors, lambdas. This is like A lambda 1, A lambda 2 to the A lambda n. So you can say that, bet. According to the definition that I had, you see AP1 is what? Is a lambda 1 P1. Because the P1 is just like X, AX equal to the lambda X. It's the same for the second one. AP2, P2 is the eigenvectors, so it's going to be what? It's going to be lambda 2 P2. We get to the 8Pn is going to be equal to the what? Is equal to the lambda n Pn. The definition of the eigenvalues. Substitute. So what we have? We have the product of A times B. Now this product would be changed into what? It would change to the lambda 1 P1, the first column, lambda 2 P2, the second column, up to the lambda n Pn, that is the n column. Okay? Remember, they are scalars. They are the other one is a vector. So you can break it into the product of two vectors. Look at this one. We can get a matrix P1, the first column, P2, the second column, up to the Pn. It's the first matrix. Now you multiply by this matrix, a matrix that the first column is a diagonal matrix. Lambda 1, lambda 2, up to the lambda n, everything else equal to 0. Okay, it's a diagonal matrix. When you multiply them together, you see, if you multiply this one by this matrix, when you multiply the first row by the, okay, this is going to be the first row and the first column, the only thing that you are going to get is lambda 1 p1, because everything else is 0. If you multiply by the second column, in the second column, the only thing that you get is p2 lambda 2 or lambda 2 p2. Everything else is 0. That's it. What is this? This is the matrix P. What is this? The matrix D. So what I prove? I prove that the AP is equal to the PD. Okay, AP equal to the PT. P is invertible, so if you multiply both sides by P inverse, so that give a P inverse of the AP equal to the P inverse of the PD. This part is an identity, and we did it. So we get the P inverse of AP is equal to D. A is similar to the D. Very nice proof, very nice one. Okay, that will prove that if you give me a matrix, I can show you that I can do this matrix. I can make it as a diagonal one. So I can find a matrix D so that A is going to be similar to P. You know that this is the definition of the similarity. Okay, great theorem. But your action is we give you one matrix, you just do this one for us. Okay, exactly as I did. I explained it again. You see, this is how I construct it. I start with the eigenvalues. Okay, then I find the eigenvectors. Okay, so these are the we start with the eigenvalues, lambda 1, lambda 2 to lambda n. We form the eigenvectors, P1. We didn't call them X. P1, P2 to the Pn. We put them as the column vectors and we introduce the P. Introduce the P in practice, what we do is, this is going to be the P. The diagonal matrix D is going to be matrix whose entries are going to be eigenvalues. Then automatically we know this one. But sometimes in the problems, they ask you to confirm it. So you have to confirm it that this condition is satisfied. Okay, you can do this one or you can do this one. I'll show you in a minute in the problems that we are going to have. That's it. Nice theorem. Okay, so and that makes things so easy for us. So let's see, give you one example. The important part is just be able to do it for us. Okay, let's see. We can go with the 2 by 2. Let's go with the 3 by 3 mostly. 2 by 2 is easy, but you will see them. But I would like to give you one 3 by 3, so it's a main course. It takes a little bit time, even on the test. Manage your time. It's nice, and you know it can be done. Everything we talk about it so far is going to be used. Okay, so this is the problem. Example. They give a matrix and I ask you to do it. That's it. Find a diagonal matrix. They break it into parts so that you will be forced to find that P for us. Okay, find a diagonal matrix. Diagonal matrix similar to the matrix A. To the matrix. Okay, similar to the matrix A. And this is the matrix 1, 0, 0, -8, 4, -6, and this must be a -8 again, -8, 1 and 9. This is your main job in this section. Be 1 on your next test and 1 on the final. Okay, there you are. So exactly as we did with this theorem, we're going to do it step by step. Okay, step 1, finding the lambdas. Solution. Step one, find eigenvalues. This is step one. Find all eigenvalues. Values of A. That's a step one. Okay, you know what does it mean? This means you have to form, this is it. You are going to, let's say, solve, just for your information, determinant of lambda I minus A equal to the zero. This is how we find the, okay, the lambdas. We're going to form this one. We already talked about the other day how we're going to do it. This is going to be the determinant of the A, lambda I. Okay, lambda I minus A equal to, we go to this one. On the main diagonal, you change the signs and the lambdas would be in the main diagonal. So this is it. It's going to be lambda minus 1. Everything else, you change the signs. These are 0. So it's going to be no change for the signs. The second one, you change this sign, is going to be 8 lambda minus 4. And over here, you change the sign into the positive. Okay, over here, you change the sign, 8. You change the sign, -1. And this is going to be lambda minus 9. The lambdas are going to be coming on the main diagonal. Okay, so this is going to be the matrix. It's going to be a determinant. Okay, so you know that you have to use the determinant, or just suppose these are just a straight line. This means determinant. I don't have to rewrite it again. Okay, you want to let this one to be equal to the 0. So we are going to find the determinant of this matrix. It's easy. Just go with the first row and find it right away. So this is going to be lambda minus 1. Okay, you eliminate these two. Okay, this is it. Eliminate these two times it by. So it's going to be times it by what? Times it by lambda minus 4. Lambda minus 4 times lambda minus 9 minus, this is a -6, is going to be +6. Check these signs, make sure you don't miss it. Equal to the 0. Simplify the inside first. So this is going to be what? Void. It's going to be lambda square minus 9 lambda minus 4 lambda plus 36 plus 6 equal to 0. Simplify. That gives me lambda minus 1 times, what's that's going to be lambda squared minus 13 lambda plus 42 equal to the 0. Try to see if it's factorable. Most of the time this is going to be the case. Two numbers with the product of 42 and the sum of 13. So that gives a lambda minus 1 times lambda minus 7 times lambda minus 6 equal to 0. So we have three solutions. You may call them lambda 1 equal to the 1. That's the first one. It doesn't matter which one are going to call lambda 1. That's a lambda 2, and this is going to be lambda 3. This is a step 1. Okay, step 1, finding the eigenvalues. Remember that matrix D eventually, that diagonal matrix would be, this is the one, 17600 everywhere else. But we want to get the procedure, okay, the P that's the first step. So now we need the eigenvectors to be able to form the matrix P. Okay, so the next step, find all eigenvectors. Okay, eigenvectors corresponding to, you know, to these numbers, to eigenvalues, to the, you do it right away. I just give you the instruction to the eigenvalues. So we start one by one and take care of it. Let's start with the lambda 1 equal to 1. You know that, and instead of this determinant, you have to form the system of lambda I minus a times x. And this would be what? This would be equal to the 0. And then you have to find the vector x for us. Okay. So I'm going to go to the next page because I need more rooms. to be able to do it. So I start from here and I change the lambda equal to the 1 here. Okay, so this is what you need. Let's start with the lambda 1. Okay, so what's a lambda 1? Lambda 1 is equal to the 1. You are going to form this one. You are going to form the lambda 1I minus A times X equal to the 0. This is going to be the system. It's going to be system, and this X is going to be three-dimensional. Eventually, we are going to call it P1, of course, okay? It's going to be X1, X2, X3. We find it, then we call it P1. Okay, go back to that system and substitute lambda equal to the 1, so that give you 1 minus 1. Okay, 0, 0. And this is going to be 8. 1 minus 4, 6. Then you get the negative 8, negative 1, negative 8, negative 1. And that was 1 minus 9. 1 minus 9. And this is going to be multiplied by your x, which is going to be x1, x2, x3. And this is, of course, equal to the 0 matrix. Okay, remember where I put them? I put it here. It's easier to get this part. Okay, now we have to work. Let's simplify it first. If we simplify it, that would give us 0, 0, 0. And this is going to be 8 minus 3, 6. And this is going to be negative 8, negative 1, and the negative 6. Okay, so this is, sorry, negative 8. Negative 8. Okay, this system is going to be a dependent system, but you have to change it to the row echelon form. You know that this is a kind of augmented matrix that we are going to have. Okay, so we need, we just replace this one because we need to start with the 1. Okay, so I'm going to switch these two together. Okay, so we are going to, what I do, I switch the R1 into the, let's work with this, okay, this matrix only first. So I'm going to switch this one, R1 and the R3. So I start with the negative 8, okay, is a negative 8 minus 1 minus 8. Then this is going to be 8, negative 3, 6. And this is going to be 0, 0, 0. Okay, work in this one first, change it to the echelon form, and then go back. Okay, so what can I do is I need the 1 here, so just divide this one by negative 8. So this is R1. I change it into the negative 1, 8 of R1. Okay, so that give me, okay, so what we are going to have is this is going to be the case, and the second one I can change the second one too, or let's do the first one first. And because we need to to make this one 0, so what we can do is we can add them together. Okay, it's going to be R2 added to the R1 at the same time. So this is it. We end up with the 1. Okay, we divide by 1, 8, negative 1, 8. So that gives us a 1, 8, and this would be a positive 1. The second one, R2 and R1 add together, 0, negative 4, and this is going to be a negative 2, and we have the 0, 0. Okay, so we got the 1 here. So we change this one to get the 1 in the second one. So this is going to be R2. We change it into the negative quarter of the R2. Then we be almost done. Okay, so we have the 1 over 8, 1. If you divide this one, that gives us a 0 and 1, and that gives us a 1/2. Okay, 1/2, and we have a 0, 0, 0, 0, 0. Okay, so this is it. You need to make this one into the 0. So you may go with the R1 equal to the R1 minus 1 over 8 of R2. Okay, and then that will give us what we need. Okay, this is going to be 1. Now we get the 0 here. Negative 1, 8, make this one into the 16. And this is going to be 15. We get a 15 over 16. 15 over 16 and 0, 1, 1 half, and the 0, 0, 0. Okay, so that gives you the row echelon form that we're going to be interested in. So you multiply by x1, x2, and x3, and this is where you want it to be. You want it to be 0, 0, 0. This system is always independent system. You know that this is 0, so you have to pick one of the variables to be free. So we pick the x3 to be equal to the t. Okay, then we have the x2 here. Okay, so that's going to be x1, x2, and x3. Okay, so what we have? We have the x2 is going to be x2 plus 1 half of, okay, we have the x2 plus 1 half of x3 equal to the 0. So from here, x3 is t, so x2 would be negative 1 half of the t again. Okay, and from the first one, we get the x1. Okay, you get the x1 plus again 15 over 6 of the x3 equal to the 0. So your x1 is going to be equal to what? Equal to the negative 15 over 6 of t. Okay, so they are all depend on t, but you are interested in one of them. So what we do is, this is going to be our vector. So the vector x1 is negative 15, 6 of t, and the x2 is negative 1 half of t, and the last one is t. Okay, you can pull out the t and pick the leftover that we're going to be interested in. It's a no, you get infinitely many vector, but you are going to pick only one of them. This is it. So the negative 15, 6, negative 1 half, and 1. You can pick this one as your vector, or you can multiply by a number to get, to get something nice. You don't like to have the fractions, okay? So what you can do is you can take the t equal to the 6 if you like, so that we're able to simplify it a little bit, okay? So if you simplify it, oh, I'm sorry, it's not 6, it's, oh, I'm sorry. That's a 16 somewhere. I said 16, but I didn't write. Because 1/8 of R2 would be 16. Okay, so that's going to be 16. And this is going to be 16. And 16, 16. Okay, you can avoid the fraction. Avoid the fraction by taking the t to be equal to the 16 to find one of your solution, okay? If you take t equal to the 16, so your first vector, we call it P1, remember, is going to be 15 or negative 15. Okay, doesn't matter. So I take it to be 15, 8, and negative 16. Or, I pick the t to be negative 16. You can pick, any other number you like. It doesn't matter. That give you the same answer. Okay, so you got to be patient to get through these, okay? Because this is the first one. We have 2 more to go. Okay, so it's going to be independent system. 2 by 2 is quick, and most of the time this is the one we have, but it's not guaranteed. You should be able to do a little bit higher for us. Okay, so this is the first one. So we check the first eigenvalues, lambda 1 equal to the 1, and then we get the eigenvectors as p equal to the 15, 8 to negative 16. Now let's go and check the other quickly. The other eigenvalue is lambda 2 is equal to the 7. So you have to solve this equation. 7i minus a times x equal to the 0. Okay, go back and form that matrix again. So it's 7i minus a is going to be equal to times x is equal to the matrix. Remember the one that we did before. This is it. Replace the lambda by 7. 7 minus 1, 7 minus 4, 7 minus 9. So that is going to be the result. So if we put the 7, so that gives us 6, 0, 0. This would be 8, 3, 6. And this is going to be negative 8, negative 1, negative 2. Okay, negative 2. And we have a matrix, and we have a vector x1, x2, x3 equal to the 0. Okay, do the same thing. Take this matrix out, change it to the row echelon form, and pick your vectors. Okay, so I'm going to take this one out to work with it. So what I do, I automatically, let's rewrite it here. So this is a matrix that I have to change. 8, 3, 6, negative 8, negative 2, 1, negative 2. I need a 1 here. That's easy. I change it into the 1/6 of the R1. Okay, that would be helpful. And I just add these two together so that I get 0 here. Okay, so at the same time, I'm going to change the R3 into R3 plus R2. Okay, so what's going to be the leftover? I'm going to have the 1, 0, 0. This is going to be 8, 3, 6. And this is 0, 2. Okay, 0, 2, 4 so far. Okay, so what I got is, I got the 1 here that I want. And so what I need to do is, I need to change this one into the 0 to continue. Okay, that is going to be easy. So it's going to be R2. I change it to the R2 minus, minus 8R1. That quickly give me the, okay, this is going to be the leftover. It's going to be 1, 0, 0. So let's make it into 0. And this is going to be 3 and the 6. Okay. And I have now 0, 2, and 4. Okay, so I can simplify this quickly. We simplified by changing this one into what? This is R2 into the 1/3 of the R2. You can do some of them at the same time. R3 into the 1/2 of the R3. So that gives you a nice matrix. So I have the 1, 0, 0. This gives me 0, 1, 2, and that would be 0, 1, 2 again. You see? Quickly, you are going to get the R2 into R3 into the R3 minus R2, and then you'll be done. So we have the 1, 0, 0. It's going to be 0, 1, 2. Now over here, we get the 0, 0, 0. There you are. This is going to be your row echelon form. Okay, bring the matrix. This is going to be 1, x1, x2, x3. And this is equal to the 0, 0, 0. So as you can see, you have to pick the x3 to be free variable. So we pick the x3 to be equal to the t. Okay, that's going to be x3. From the second one, So that's going to be your x3. From the second one, you have the x2 plus 3x, sorry, plus 2. Plus 2x3 equal to the 0. So your x2 is going to be negative 2x3. So that gives you your x2 equal to the negative 2t. This is going to be your x2. You go to the first one, and for the first one, we get x1 equal to the 0. Okay, this is the first one. x1 equal to the 0. So we are going to have the second vector that we are going to be interested in. Okay, so this is it. We have x1. x1 is equal to the 0. x2 is equal to the negative 2t. And x3 is equal to the t. You can factor out the t then as a basis if you like. So it's going to be 0, negative 2, and 1. So that gives you the second vector that you are interested in. So that's the second column of a matrix P. So that gives you 0, negative 2, and 1. Okay, so this is P1 and the P2. We need one more. Okay, so what we're going to do it again. Lambda 3. Lambda 3 is equal to the 6. Okay, go back again, go back to the original one that we talked about it, substitute for the 6 to get your vector. Okay, so this is it. So you have to form lambda 6i minus a times x equal to the 0. 6i minus a, if you go to that matrix, is going to be what? So this is going to be changed into the a matrix. This time it's going to be 5, 0, 0, 8, 2, 6, and the negative 8, negative 1, and negative 3. Okay, negative 3 times it by x1, x2, x3. You can summarize it, don't write everything, but it's nice to know. So this is going to be matrix in question. Okay, take this thing out and simplify it to get the result that we are interested in. We just divide this one by 5 quickly to get the number. So this is going to be the matrix in question. You have to work with this one. And this is again 8, 2, 6, and the negative 8. And this is a negative 1 and negative 3. Okay, this is the matrix in question. So we are going to divide the first part by 5. So R1 is 1/5 of R1. Again, as we did it for the other one, it's R3. You change it to the R3 plus R2. So the leftover is going to be, we get the 1, 0, 0. This would be 8, 2, 6. Okay, 8, 2, 6. And if you add, we get the 0, 1, and 3. Okay, 0, 1, and 3. This is going to be the case. Okay, so if we get the 1 over here, switch these two, and then quickly you can get it. Okay, so this is it. Switch this two, R1, sorry, R2 and the R3. So this is going to be 1, 0, 0. So it's going to be 0, 1, 3. Okay, 0, 1, 3. And did I miss anything? That so what I did is we just okay, R3 and R2 that give you 0. This is going to be 1, and this is going to be 3, which is true. Okay, now we have to get rid of these 8, and we can do it quickly. Nothing to worry about. It's going to be 8, 2, 6. Okay, 8, 2, 6, and what we can do is we can add it to the first part to get rid of the 8. So R3 is going to be R3 minus 8. Okay, R1. And if you do this one, so the first one's going to be 1, 0, 0. The second one's going to be 0, 1, 3. And the last one is going to be what? So the last one's going to be 0, 2, 3, which is the same as the, okay, which is the same as the second part. Okay, and that's of course 6. Okay, so this is it. You check this R3 into the R3 minus 2R2. So the result is going to be this matrix 1, 0, 0, 1, 0, 0. This is going to be 0, 1, 3, and you get the 0, 0, 0. Then you can pick your, okay, your matrix. So this is times x1, x2, and x3, which is equal to the 0, 0, 0. Okay. So we can pick the x1, x2, x3 here. Again, x3 equal to the t. This is going to be x2 plus 3t to get the result. Okay, so let's do it. So I get it from here, and I'm going to find those my x3 would be t. This is going to be x2 plus 3, like the previous one that we did. So this is going to be the conclusion. x3 is free, so I'm going to call it t. Okay, from the second part, I have the x2 plus 3x3 equal to the 0. So that give me x2 equal to the negative 3x3, which is a negative 3t. Okay, and I go to the first one, that give you the x1 equal to the 0. So the matrix in, okay, in few question, the vector in question is going to be x1 is equal to the 0, x2 is a negative 3t, and the last one is t. Pull out the t. If you pull out the t, that gives you 0, negative 3, and 1. So this is going to be P3. So the P3 is going to be equal to 0, negative 3, and 1. Okay, now we are ready to give you the matrix P. Remember, the matrix P is going to be the matrix whose columns are going to be P1, P2, P3. Okay, so there you are. The matrix P is going to be a matrix with these columns P1, P2, and P3. So the matrix P is equal to, the P1 was 15, okay, 15, 8, negative 16. P2 was 0, negative 3, and 1. P3 is 0, negative 2, and 1. This is P. What is the diagonal matrix? Remember, it's a matrix whose diagonal are eigenvalues. 1, 6, 7. Anywhere else is going to be 0. Remember, these are going to be 0, 0. So again, one can show, if you like, one can show that. Sometimes they ask you to show this in your book. Show that P inverse, that condition, P inverse of AP is equal to the D. You can show this one, or you can show that A times P is equal to the P times D. This is easier if they ask you, okay, if they ask you to show it, to get these numbers, okay? I give you one of them, then if you like, you can check the other one yourself. So PD, this is P 15, 0, 0, 8, negative 3, negative 2, negative 16, 1, 1. It's easy to multiply by D, of course. The D is 1, 0, 0, 0, 6, 0, 0, 0, 7. Okay, quickly you can multiply, because when you multiply, you get only these numbers. If you multiply, you get 15, 15, 0, 0. Then you get 8, negative 18, negative 14. And the last one, we get negative 16, 6, and 7. You see, this is going to be P times D, and the AP is the same. You can check it for yourself, that the AP is going to be the same thing. You see, 15, 0, 0, 8, negative 18, negative 14, and the negative 16, 6, 7. You see, in some of the problem in your book, they ask you to confirm it. But on the test, we are going to ask you to find the P. If you find the P, that's enough for us. But if you want to make sure that this P is the correct answer, you have to check these two conditions to make sure that they are equal to each other. If they are equal to each other, this means you got it. Okay, so I just picked one example that takes time, so I wanted to show that you know how much you to put into it if you like. Most of them are 2 by 2, but the other option is 3 by 3. So you must be able to take care of one of these for us, 3 by 3 on the test. Okay, we are going to give you one 2 by 2 and one 3 by 3. Okay, and this is the 3 by 3 one. It's very smooth operations. And there are a couple of tricky one. I give you one more next time. That would be too much. I try to give you everything tonight so that you'll be able to have them in one setting. Okay, then we are going to give you another, I make another one for you. Then would be kind of what is the applications. There is something else that we have to do. And that's the one that we promise. Say that we can use this one to find the power of a matrix. So, you know, just would be a short one. So this is going to be the one. Probably this is how we are going to give you this. You know, we take you through the next week. We give you a review for your test. We give a little bit more time to practice. This is going to be our last test from before the final. And of course, you can drop your, you know, lowest test. But it would be good to get these because these are going to be repeated on the final. The other things that we are going to do later is these are real numbers. If it's going to be complex numbers, it's the same procedure, but you got to be very patient to get through those complex numbers. Otherwise, you got the main idea really. This theorem is quite important one in linear algebra. Okay, so read it carefully. I just put them everything in one setting, but I come back and give you more example and more details of these ideas. Okay, if you have any question, you just let me know. If you want to come discuss it on the Zoom, we don't mind. Okay, that's it. Have a good one. Take care, and see you at the next time. I'll give you another one. Probably I leave it for Monday. And I post the practice test. So during the week, we can go over the solution to the practice test. Okay, just to prepare. Okay, bye-bye. Take care.